So in a moment we're going to balance redox reactions. Before that, let's just take up these last three questions with regards to finding oxidation numbers, because finding oxidation numbers is the key to balancing redox actually. So here we have H2SO4 aqueous. So hydrogen, this is not hydride, so it's going to be a +1 oxidation number. Oxygen -2, and so sulfur X is what we need to find. So whatever X is, plus 2, because there's 2 hydrogens, plus the negative oxidations due to the oxygen, so -2 times 4, all that has to equal to 0 because sulfuric acid is neutral. So you solve for X and you end up with X is equal to +6. Over here, with Fe2O3, oxygen is -2 because it is not a peroxide. And so there's 3 oxygens, and so altogether this is a 6- charge. So the iron must be 6+. But there's 2 of them, so 6 divided by 2 is +3 is the oxidation of the iron. Now, this last one I said before, it's a little bit tricky. Oxygen is -2, and there's 4 of them, so altogether that's -8. So altogether the positive charge must be +8. However, there's 3 irons, so 8/3 is actually going to be the oxidation. I'll put a little explanation point because perhaps that's surprising. Now, 8/3 in decimal notation is 2.66 and so on. So you might think about what that means. Well, probably you know that iron can have 2 different oxidations. Actually, well, it can have probably more than 2, but the 2 common ones are 2+ and 3+. So 8/3 probably means that there are 2 Fe3+ and 1 Fe2+ within this formula over here. And so you can see 3 + 3 + 2 is 8, and that makes a total of 8+ divided by 3 gives you this oxidation number of 8/3. And if you had to figure this out and use that oxidation number, that's what you would use. I wouldn't worry too much about what that means, although we've talked about it a little bit. You just use that number and proceed with the question. So let's begin some balancing redox. Here's a question, and I copied the question because the most important thing we need to get out of it is that it is acidic. These are the rules that we're using. They're on page 667 of the Nelson book, and you can see later on we're going to uncover some other rules for basic solutions, but this one here is acidic. So here's our equation, and I always recommend you set it up. This question was intended to be balanced by half reaction, but it works just fine to balance it using oxidation numbers. So set it up like this. We have your change of electrons per atom, change of electron per reactant on the side. So first thing I do is I go through and I figure out the oxidation numbers. With iron, it's 2+, so obviously that's going to be +2. With chromium, it's going to be +3 because the ion is 3+. Iron here is pretty obvious. And this is the only one where we have to do a little bit of algebra. The oxygen is going to be -2, and so we need to solve for the chromium. And there's 2 chromiums, so 2x -14 because of the 7 oxygens that are each -2. And all that has to equal -2 because that's the charge on the ion is -2. And so when we do our algebra here, we end up with x being equal to +6. Okay? So now we take a quick look at this, and we notice that the loss of electrons, the oxidation, is between Fe2+ and Fe3+. There is our Leo. And the GER, the gain of electrons, is between the chromium going from 6+ to 3+. That's the gain of electrons there. And so now, the iron then, going from 2+ to 3+, that's a change of 1 electron. And the chromium going from 6 plus to 3 plus, that's a change of 3 electrons. To figure out the next line, we say, how many irons are there? Well, there's just one. So we multiply this by 1, and of course the number doesn't change. But here there's 2 chromiums, so we multiply by 2, so it's a change of 6 electrons. Now, the next part is to determine what our coefficients here are going to be. And we multiply this by 6, so that there is 6 electrons transferred to balance out this 6. We multiply this side by 1. So the 2 coefficients that go there are going to be 6 and 1. All right, so now we've done all the steps up to about here. Okay, now actually there's 6 irons here, then there's going to be 6 irons here, and there's 2 chromiums, so we put a 2 here. So the next thing we do now is we need to think about the oxygens, balance those using water. So there is 7 oxygens on the left, so we balance the right side by adding 7 waters. And we can do this because this is occurring in acidic medium, which is an acidic aqueous solution, so we're perfectly justified in doing that. And the last thing to do is to balance the H atoms using H+. So there is 14 H+ on the right, and so we add 14, there's 14 hydrogens on the right, so we add 14 H+ on the left. And we're allowed to do this because this, of course, occurs in acidic medium. And there we are now, we're done. We can check the charges. The charges should balance, and all of the atoms should balance. So now we're going to balance another equation, and this one is one that occurs in basic medium. So this is why I've copied the question, because it says basic. So this is important because we're going to have to do these extra steps here. So I figured out all the oxidation numbers there already to save time. But let's figure out where the oxidation is and where the reduction is. So it looks like carbon is going from -2 to +4. So that is a loss of electrons, which is an oxidation. And the GER, the gain of electrons, is between manganese going from +7 to +6. Okay. So that is the GER. So now we take a closer look, and with the carbon then, from -2 to +4, that's a change of 6 electrons. And with manganese, from +7 to +6, that is just 1 electron. So I write that underneath each reactant. There is only 1 carbon in this formula, so this number is going to stay the same, and there's only 1 manganese in this formula, so this number is also going to stay the same. So that means that we need to multiply this side by 6 and this side by 1. So that tells us that these coefficients over here are going to be 1 and 6. And so now we balance all the elements other than the oxygen and the hydrogen. And since there's 6 manganese here, we're going to put a 6 here. And there's 1 carbon on each side, and so we're done. And now we move on over here with step 5, oxygens by using waters, because of course this is in basic medium, so it's a solution. So there is 1 oxygen here and 24 oxygens here. And it's really useful to use a chart like this if you need to. So total of 25 oxygens on the left, and on the right side we have 3 plus 4 times 6 is 24, for a total of 27 oxygens here. So that means we're adding 2 waters on the left side. And now with the hydrogens, there is 3 plus 4 plus 1, so a total of 8 on the left side. And so we'll be adding 8 H plus to this side. All right. Now, at this point, we'd be done, except this is not acidic, it's basic medium. So we have to do these additional 2 steps. The first step says add hydroxide to eliminate H pluses. So we can add 8 hydroxide here, so long as, of course, we add 8 hydroxide here. And then it's a matter of combining H plus and OH minus to see what cancels out. So these 8 together will make 8 waters. However, it's supposed to be liquid. We already have 2 waters here, so these 2 waters will cancel 2 of these waters. So in fact, we only have 6 waters on the right. And so there's our final solution, although it's not a bad idea to rewrite it neatly. And so I rewrote the solution neatly and put it in a box so that it's obvious what the final answer is. And once again, if you wanted to, you should check the charges on both sides, and they should be equal. And you could check all the atoms on both sides, and of course they should be equal, because that's required in any balanced reaction.